Okay, let's look at a couple of problems here. So first of all, let me define launch angle. Launch angle is the direction of the initial velocity. So if you have a zero launch angle, that means that you're just rolling off a table or moving horizontally through the air. And your initial velocity is only in the x direction. So imagine that you have this diver and she's launching at 15 meters per second horizontally from a 100-meter high cliff. And we want to know how long she's in the air. So imagine what's going on here. This thing is, she's going off horizontally. So initially, in the y direction, she has 0 speed. Gravity is negative 9.8 meters per second squared. And her change in y is negative 100 meters. And we want to know how long she's in the air. Now let me note that change in y is negative because she's falling, right? And delta y is a vector. She's falling and is going to fall 100 meters below where she started. So we have to plug that in as a negative 100 meters. And we're looking for the time. So the formula that we would use would be a formula with vi, g, y, and t in it, or delta y equals vit plus 1/2 gt squared. Remember, vi is not the 15 meters per second. It is the initial y velocity, which is 0. So negative 100 would equal 0 plus 1/2 negative 9.8 meters per second squared t squared. And if we solve for that, we'll get 4.5 seconds. What if we want to know the components of her speed just before impact? Well, we know that she launched horizontally, so to start with, she has an initial speed which is equal to her, Vx. And there's a mistake here, so we're going to correct that quickly. Her Vx, in this case, there's no angle, so it would be equal to 15 meters per second times the cosine of 0, which is 15 meters per second forward. So her Vx is always going to be forward 15 meters per second. Her Vy is going to be 0 to start with, but what is it going to be after she falls 100 meters? So that's what we want to do. We want to figure out what Vy is right before she lands, after she's fallen 100 meters. So to do that, what we're going to do is we're going to look for Vfy, but we know that we started out with no initial Viy, 0. Gravity is always negative 9.8 meters per second squared, and delta y is negative 100 meters. So the formula we're going to need is a formula that does not have time in it. It's Vf squared equals Vi squared plus 2Gy. If we plug in all our numbers, we should get a Vf, and when we take the square root, 44 meters per second. But remember, we're falling down, and when you take the square root, you can have a negative root. So it's a negative 44 meters per second. So her components right before she hits the water, not when she hits the water, but right before she hits the water, are Vx are 15 meters per second and Vf are 44 meters per second in the negative direction. The last thing we want to do is find her range. Her range is how far along the x-axis, or how far out did she land. There's only one formula with range, and that is the only formula that we have for horizontal motion. And once again, I used the wrong number for that. It's Vx times t, which should be 15 times 4.5. So, that should be, just give me a second here while I calculate that for you. 15 times 4.5, which is 67.5 or 68 meters to 2 sig days. About 67.5 or 68 meters to 2 sig days. All right, so if you're looking for something that's horizontal, you want to use a horizontal equation. But if you're looking for time or speed for VF, a vertical thing, you're going to use the red equations. How would it change if you had it not launched at 0? So let's say we imagine that we kick a ball at 100 meters per second at an angle of 30 degrees. And we want to know how long it's in the air. Well, first we need to resolve and find out what its V. Remember, if we're going to find how long it's in the air, we need to be looking at what's going on with Vy. Vy starts out as V sine theta, 100 sine of 30, which is 50 meters per second. And it's a symmetric parabola. So this thing is going to go up. It's going to slow down, slow down, slow down. 0 at the very top for Vy, and then as it goes down, as long as it lands exactly where it was launched from, its Vy will be the same number, but it'll be negative. And gravity is negative 9.8 meters per second squared, and time. And so the equation that has all those variables is Vf equals Vi plus Gt. When you plug in your numbers, making sure to plug in a negative 50 for Vf and a positive 50 for Vi, and a negative 9.8, you get 10 seconds for the time in the air. How high does it go? So once again, the velocity that determines how high it goes is the high or upward velocity, the Vy. So delta Y is what we're looking for. He was launched at 50 meters per second upward. At the top, that's where we're going to stop. We don't have to go all the way down. So at the top, he has a speed of 0 in the Y direction. Gravity is always negative 9.8 meters per second squared. The equation that has all those variables is Vf squared equals Vi squared plus 2Gy. And when you do that problem, you should get 128 meters. Notice that you have a negative 9.8, and that when you subtract negative 2,500 from both sides, you're going to get negative 2,500. So your negatives go away, and that makes sense because you're rising. You should be getting a positive delta Y to find the height that you rise, a negative delta Y to find the height that you fall. And then lastly, if I want to find the range, it's Vx times t. So first I find Vx, which is 100 cosine of 30, which gives me 87, and multiply that by the time it's in the air, is 10 seconds, 870 meters. So there's also a couple of other shortcut equations that you can use that allow you to, if you only know the velocity and the angle, you can find the range using the velocity that you threw it up squared divided by gravity times sine of 2 times the angle. And that means that there's actually a couple of different, because there's a sine in there, there's a couple of different angles for every range. So for example, if I launch it at 30 degrees and I launch it at 60 degrees, I'll get the exact same range. The math will work out. And you notice 30 plus 60 adds up to 90. So angles that add up to 90 always give you the same range. So if you're in ballistics and you need to hit something, but there's a big tree in the way, then you can maybe use a bigger angle to avoid the tree or a smaller angle to avoid something. So if angles add up to 90, they always have the same range. And 45 degrees is going to give you the maximum range. So one more thing to remember, there's a lot of symmetry in projectile motion, and when you're solving these problems, use it to your advantage. When I did the projectile launched at an angle, I found Vy going to start with, and that Vf in the Y direction was negative. So if I throw it up at 50 meters per second, it will land at negative 50 meters per second. Because we don't have air resistance, projectiles are symmetric. If it takes 10 seconds to rise and fall, then it only takes 5 seconds for half of the trip. So make sure that you can find the components of your initial velocity, and that realize that they are happening at the same time, but they do not affect each other directly. And that the acceleration is always in the negative 9.8 meters per second squared direction, it's always acting down. And that if the launch angle is 0, then the initial velocity has only an x component. There is no Vy component. And that the path followed by projectiles is parabolic, and thus it is symmetric. And that the range is defined as the horizontal distance that the projectile travels.